have been talking about solid liquid separation, and we will continue with the same topic today as well. The most important equation is the Darcys law, and the Darcys law relates the throughput that needs to be filtered or the velocity of the liquid flow as a function of the pressure drop, the surface area for the filtration as well as the bed thickness. So the viscosity of the fluid and the bed thickness are contributing in an inverse fashion towards the rate of filtration, whereas the pressure drop and area of the filtrate contributes in a direct manner towards the rate of filtration. So in the last class we saw that the Darcys law appears like this: velocity is equal to K, that is a constant, delta P, that is the pressure drop, mu is your viscosity of the medium, and B is your bed thickness. So it is a very simple equation and it assumes certain conditions, especially relating to the Reynolds number. So the Reynolds number has to be within certain region, then only this law is applicable, otherwise you have a very concentrated slurry and it might not be applicable at all. So the Reynolds number has to be less than 5, and the Reynolds number, as you know, is defined in this particular fashion. That is the diameter of the particle d, the velocity of the fluid flowing, rho is the density of the fluid, mu is the viscosity of the fluid, and in addition we also have a term called 1 minus epsilon. Epsilon is the porosity of the bed. So this is how the Reynolds number is calculated, and the Reynolds number should be less than 5 for Darcys law to be valid. But then although the Reynolds number needs to be less than 5, we still use this equation as a first approximation to calculate the throughput of the filtration process. So we can use this model for doing a lot of calculations. We can use it to calculate what should be the time to filter a slurry of certain volume, or conversely if we decide on the time we can calculate the area required for performing this particular filtration process, and that is what we will try to derive. That is the equation which we will try to derive actually. So if you are looking at velocity of flow through a bed and the volume of the liquid that need to be filtered, then the velocity and the volume will definitely be related to this, that is velocity is equal to dV by dt, where V is the volume and T is your time. So dV by dt is the average rate of filtration, and the whole thing is divided by area. A is the filtration area. So if the filtration area is very large, then the velocity will be very less. Okay. So we can use this equation to do lot of things. So we can introduce this equation into Darcys law, and then we will end up with the differential equation for average volume of filtration for a given time as a function of the delta P, that is the pressure drop, A is your area, and B is your bed thickness, and mu is your viscosity of the medium. Okay. Now there are several assumptions which we need to make before we actually solve this particular equation to arrive at something meaningful. The first assumption is we will assume that the filter cloth or the filter medium does not offer any resistance. So if you assume that, then it is very simple for us to integrate this equation and arrive at a relationship for time as a function of all these parameters. So we will assume that the filter cloth does not offer any resistance, number 1. Number 2, sometimes the bed itself can offer resistance if increase the pressure of filtration process. So if the bed pressure increases as we keep on applying an external pressure, then it is called a compressible solid. That means as we keep increasing the pressure, the bed gets more compacted, so that is called a compressible solid. Especially solids like clay, chalk, they get compressed when you apply a lot of pressure. So they are not very good if you want to apply a lot of very high pressures, whereas on the contrary if you take sand, even if you apply very high pressure, sand will not get compressed because they are very porous. So in such situations, by increasing the pressure we will be able to increase the rate of filtration. So for uncompressible solids the rate of filtration can be increased by increasing pressure, whereas if it is a compressible solids like clay or chalk, by increasing the pressure you are in trouble, you will be reducing the flow because the material gets compacted. So when we assume the solids are incompressible, that means there is no change in the porosity if I keep increasing the pressure across the bed, okay. Then we can say the BD, the bed thickness, as a function is equal to rho naught. Rho naught is a term which is defined as mass of cake of solids per volume of filtrate multiplied by V is the total volume divided by the area. And if you assume the specific cake resistance as the capital which is equal to the capital sigma C is equal to 1 by K, K is your constant which I defined in the Darcys law, then we will end up in integrating this Darcys law by assuming at t equal to 0 the volume that is filtered is 0. By doing that we can get a relationship for the time required to filter a volume of liquid V in a batch unit. So this time is a function of many parameters, the volume that needs to be, volume of slurry that needs to be filtered, mu is the viscosity of the medium, rho naught is the mass of cake of solids per volume of filtrate, A is the area of the filtration unit, delta P is the pressure we apply. So you see this equation is obtained by assuming many situations. One is we assume that the filter cloth or the filter medium does not offer any resistance, number 1. Number 2, we assume that the solids are incompressible, okay. And then number 3, we assume an average rate of filtration, that means we assume dV by dt which is average rate of liquid that is filtered over a period of time. So by assuming these 3 we end up with the relationship for the time of filtration to filter a slurry volume of V, and these are the physical properties of the slurry as well as the liquid, that is mu is the viscosity of the liquid, rho naught is the mass of cake solids per volume of filtrate, as you keep filtering, A is the cross sectional area and delta P is the pressure. So with this equation we can do many things. So if I know how much liquid or slurry that needs to be filtered, and if I know the area of the filter unit, I can calculate how long it will take to filter. Or conversely, if I want to filter a slurry of volume V in certain given time t, what should be my area of the filter unit, I can calculate from this equation. So I can do both, I can use it as a design equation or I can use it as a simulation equation, and this is a very interesting equation because by assuming several conditions we got a very simple equation, and it is very useful to make use of this equation for calculating the time of filtration or area required for the entire filtration process. Okay, now if the cake is compressible, previously we assumed that the cake is incompressible, but if you assume that the cake is compressible, then as we increase the pressure the resistance also increases because the material gets compacted. So we write an equation for the constant like this, where S is a exponent which may vary, and generally it is about 0 to 0.8. If it is highly compressible we will take S as almost equal to 1, if it is not at all compressible, that is if it is incompressible, S will be 0. Okay. So you see that this particular equation mentions that the resistance offered by the cake towards the flow of the liquid is directly proportional to delta p raised to the power some exponent, and generally we can take this exponent around 0.6 or 0.7 or 0.8 and so on. So in such situations what do we do if you want to filter a material which is going to get really compacted as you increase the pressure? We add something called filter aid. Filter aid is like sienite, sand, all these. What it does, it reduces the resistance offered by the cake, that means it converts a compressible solid into partially compressible or incompressible, so that the liquid can flow through. So if you have that type of situation, then you have a term called delta p raised to the power s. Okay, let us look at a simple problem that will give us an understanding of this concept of incompressible solids as well as the compressible solid. So if you want to know whether your cake is compressible or not, what do? We perform the experiment at different pressures and then see what is the resistance offered by the cake, that means cake resistance. Okay. So from that we can find out whether the solid which you are going to filter is compressible or is not compressible. So imagine I have done some experiments and at different pressures delta p, so at different pressures delta p you get different cake resistance. So what do? You can plot the logarithm of this delta p and logarithm of cake resistance and see how the line looks like, whether it passes through the origin or whether it does not pass through the origin. So this is the relationship if you recall. So if I take logarithm of the left hand side as well as logarithm of the right hand side, what happens? You will have S as the slope of the double log plot and this term will become the intercept, logarithm of that will be the intercept. So in that problem I take logarithm and I take logarithm of delta p, and then in the x axis I plot logarithm of delta p, in the other axis I plot logarithm of the sigma. So what happens? It does not pass through the origin. So what does it mean? The material is compressible. So if it passes through the origin, that means S is equal to 0, that means the resistance offered by the cake is independent of delta p, whereas here it is not passing through the origin, right. So the plot of logarithm of this term versus plot of logarithm of delta p gives a straight line with slope s, okay, and intercept is equal to this particular term actually. So the compressibility is, from this we can calculate compressibility is 0.377. So if you are doing a filtration experiment and you want to know whether the material is compressible or not, what all you have to do is perform the experiments at different pressures and then calculate the resistance or resistivity and then plot a graph between the logarithm of delta p versus logarithm of this particular term, and then see whether the line which you get passes through the origin or not, okay. And then the slope of that line will give you this term which is called the relationship between effect of delta p on the resistance offered by the cake, okay. So if this slope is equal to 0, that means or it can be equal to 1, it can be either 0 or it can be 1. So it can take up both these values, and most of the material will always lie between 0 to 1 actually. So if it is 0, that means it is independent of delta p, that means there is no effect of pressure on the resistance offered by the cake, whereas if it is 1, that means there is maximum effect of pressure on the resistance offered by the cake. Okay. So far we talked about the filter cloth or the filter medium not offering any resistance to the flow, but there could be some situation where the filter medium itself can be offering some resistance to the flow of the liquid. Generally if you design a filtration unit, you like to keep the resistance offered by the filter medium minimum, but there are situations where the filter medium itself can offer some resistance. So in such a situation what you have, the Darcys law equation is going to be different, and the resistance offered by the cake also will appear in with the resistance offered by the filter cloth or the filter medium. Both the resistances are going to appear in your Darcys law relationship. So let us look at it again. So as you know, V equal to 1 by A dV by dt, where A is the cross sectional area or the area of the filter setup, V is your volume of slurry that needs to be filtered, and T is your time, and V is your small v is your velocity. Okay. So if you are going to have two resistances, one because of the cake, that is the RC, and one because of the filter cloth or the filter medium, then you are going to have both the term coming into the picture. Okay. So you are going to have 1 by A dV by dt delta P divided by mu Rm plus Rc. If you take incompressible cake, okay, so this term will not have a delta P raised to the power S like we saw before. So by introducing all these into your velocity equation, you are going to have 1 by A dV by dt equal to delta P divided by mu sigma C rho naught V by A. This term comes because of the resistance offered by the cake, and this term comes because of the resistance offered by the medium. Otherwise when the resistance offered by the medium is 0 or the resistance offered by the filter cloth is 0, this term will disappear. This is your original equation which I showed 3 or 4 slides before. So what do? You can now integrate this equation and get a slightly different relationship between time, volumetric flow rate, and resistance offered by the medium. Okay. So by doing that we will end up a relationship like this: A, that is the area, T is the total time required to filter a slurry of volume V multiplied by M V by A plus C. M is given like this and C is given by like this. So here you have a term which is called Rm, that is the resistance offered by the medium or the filter cloth. So if that resistance is 0, the term C will completely disappear, understand. So you will have only this relationship. This is the relationship which I showed a few slides back, because we assume that the medium also offers some resistance, we have that extra term which comes as a plus here. So interesting, if you look at this relationship, if I plot AT by V as against V by A, we will get a linear relationship. Okay. And then from the intercept of that linear relationship we can calculate the Rm term, because this is like your original equation for a straight line y equal to mx plus c. Okay. C is your intercept, m is your slope. So from the intercept we can calculate the Rm term here. So if the intercept is 0, that means this term is totally gone, that means your Rm, that means the resistance offered by the medium or the cloth is 0. But if you have an intercept, that means the resistance offered by the cloth is not equal to 0. So I just plot AT by V as a function of V by A in a graph sheet. So if the material or the cloth offers some resistance, I will get some intercept. If the material does not offer any resistance, I will not get any intercept. So I will immediately know whether the filter cloth I use is offering considerable resistance or not. So here V is the amount of liquid that needs to be filtered, T is the total time that it takes to filter that, and A is the cross sectional area of the filtration setup. Okay. So it is simple. So I take different amounts of slurry, I filter them at a constant delta P, calculate how long it takes to filter the different amounts of slurry, and then all I do is I plot a graph between AT by V versus V by A, and then I see what type of straight line I get, whether it passes through the origin or whether it does not pass through the origin. If it passes through the origin, I will say the filter cloth does not offer any resistance, whereas if it does not pass through the origin, I will know the filter cloth offers some resistance. So you can find out whether it is a considerable value or it is very insignificant. If it is a considerable value, as a design engineer you may have to select some other filter cloth or filter medium whose resistance is very small. So please keep that in mind. So if this intercept is large, then you know the filter cloth or the filter medium you use does offer some resistance. So ideally it should be as close to the origin as possible. So we saw different situations. We took the Darcys law, and then we said velocity of flow is equal to 1 by A dV d capital V by dt. Capital V is nothing but the volume of liquid that needs to be filtered. So d capital V by dt is average rate of filtration. On the left hand side you had the velocity, and then we had the Darcys law incorporated into that. Then we looked at different situations. Situation number 1 is whether the bed is compressible or incompressible. So if the bed is compressible, then the resistance offered by the cake will be directly proportional to delta P raised to the power some exponent term. That means as the pressure increases, the resistance offered by the cake also increases, and if that exponent is 0, that means it is incompressible solids like sand, whereas if delta P equal to 1, it is highly compressible and it offers some resistance like clay and so on. So as the resistance is directly proportional to delta P, as I keep increasing delta P, the resistance also goes up. So initially we looked at a incompressible cake model, and we derived a relationship for filtration time as a function of many parameters: volume that needs to be filtered, the cross sectional area of the filter setup, the viscosity of the medium, and the resistivity factor. Okay. Then we went to compressible situation, so that the resistant term gets changed, altered slightly different, and you will have an extra term of delta P raised to the power S. Then we looked at the resistance offered by the filter medium, that means resistance offered by the filter cloth or the filter plate or the filter candle. So once you assume that, your Darcys law gets slightly modified and you get an extra term, you get almost like a y equal to mx plus c, that means a linear relationship. C is the intercept which arises because of the resistance offered by your filter medium or filter cloth, and when you plot AT by V as a function of V by A, if the resistance offered by the filter cloth is appreciable, you will get an intercept, and if the resistance offered by the filter cloth is practically 0, then the line will pass through the origin. And I also mentioned that if the intercept is appreciable, then you know that the filter cloth offers quite large resistance, So you need to modify the filter cloth so that the resistance is coming down to practically 0. If the cloth is going to offer some resistance, you need to apply more pressure during the filtration process. More pressure means a larger pump means you are going to spend more money, especially in the capital cost as well as in the operating cost. So let us look at a simple problem which gives some idea about calculating filtration process and so on actually. Now it takes 90 minutes to filter a slurry of 1000 liters using a filter setup of 2 meter square area. That means area of the filtration setup is 2 meter square and the amount of slurry I need to filter is 1000 liters and it takes 90 minutes. Now I want to filter 100 meter cube of the slurry using a filter setup which has 25 meter square cross sectional area. So we can assume incompressible cake, we can assume resistance offered by the cloth is 0, assume same driving force, that means I am applying same delta P. So you know this equation which we got, this is the simplest of the equation where we assume the solids are incompressible, the filter medium does not offer any resistance. So this is the equation. So you can bring the A here, so you have T A square by V square is a constant, correct. That means you are bringing A to the left hand side, so it comes to the numerator, you are bringing the V to the left hand side, so it comes to the denominator. So T A square by V square is a constant. So initially it is given as 90 minutes to filter 1000 liters, that comes in the denominator using a 2 meter square area filter setup. So 90 into 2 square divided by 1000 square. Now this is equal to T is what we have to calculate, that is the time for filtering 100 meter cube. So 100 meter cube is as you know 1 meter cube is 1000 liters, so we have 100,000 in the denominator which is raised to the power 2, the surface area for a filtration process is 25, so you have 25 square, so you have to calculate T. So you can take these two terms to the other side, you get 5760 minutes. It is a very simple problem, but it has got implication especially during scale up. When I am scaling up from lab scale going to a pilot plant and going to a full scale commercial, the amount that needs to be filtered also keeps increasing. I might not be able to increase my filter area too much. So what is the next alternate? I need to take much longer time to filter the liquid or the slurry. So that is what is happening here. In my pilot plant maybe I am filtering 1000 liters, but in my large scale commercial plant I need to filter 100 meter cube of the liquid. Although I am scaling up my surface area of the filter setup from 2 meter square to 25 meter square, this is not enough because they are all related as a square. So it takes 90 minutes to filter 1000 liters using 2 meter square, whereas it takes 5760 minutes to filter 100 meter cube of slurry using a 25 meter square filtration setup. So which means I will take several hours to filter 100 meter cube of liquid using 25 meter square filter setup. Now we looked at simple filtration setups and we also looked at some of the equations for filtering slurry when they are compressible bed or when the bed is incompressible or when the filter medium offers some resistance or the filter medium does not offer some resistance. Now let us look at another type of filtration. I showed you a picture of that before as well. It is a continuous rotary drum filter. You have a large drum rotating slowly and there is a vacuum applied inside the drum, so the slurry gets sucked the solids get retained on the surface of the drum, liquid travels right inside. As the drum rotates, you may have washing of the cake that is deposited on the surface of the drum. So if there are any impurities which dissolves in the washing up liquid, they dissolve and get sucked in. So you have pure solids which is stuck on the top, and then that solid is scraped and collected on, and then again the drum which is free from the attached solid once again sucks in the liquid, and the solids in the slurry gets attached to the surface. So this process keeps happening continuously. So I can filter continuously a slurry, I can collect continuously wet solids. This is quite a lot used in pharmaceutical type of applications, where it happens continuously, and we continuously get wet solids which can go into a continuous dryer, and the solids can get dried and collected at the other end. So there are several steps during this process. The total filtration cycle is broken down into several steps. Step number 1, cake formation step. This is the time when the drum dips inside the slurry. So the drum is inside the slurry and there is a vacuum applied inside the drum. So the liquid gets sucked inside the drum, and the solids forms a cake or retained on the surface of the drum. This is where the actual filtration takes place. Once the drum comes out of the slurry, there is no new cake that is being formed. Please remember that once the drum comes out of the slurry, there is no new cake that is formed, but the solids are washed here. This is the cake washing cycle. I may use water, I may use some solvent which will try to remove some impurities. So if there are some impurities present in the cake, that can be washed, dissolved and removed. Again the liquid gets sucked inside, so the washing up liquid is removed. The third step is cake drying. This is the time when the moisture that is still attached to the wet bed gets sucked in. It does not get fully dried, but some amount of moisture removal takes place, and finally the solids are cut with a knife. So this is where the cake gets discharged, and the wet solids are collected for further processing, and once again the empty drum dips into the slurry tank, and once again you form the cake, and the process goes on and on and on. So here this is the cake formation step, remember that, where this is the time when the cake is formed, the empty drum dips into the slurry tank, otherwise there is no cake formed. So here we can use the same Darcys law equation and go further on. So this is the setup as I described in the previous slide. You have the cake formation when the drum is inside or dipped into the slurry, and you have a cake. Then here you are doing the washing using water or any solvent. Once again the washing up liquid gets sucked inside. This is the drying stage where the wet solid will slowly lose its wetness, because the liquid that is stuck to the solids gets sucked in, and finally here you have a cutting knife and the cake is scraped out and collected, and again the drum is empty and it dips inside the slurry tank. So this process goes on and on actually. Okay. So the cycle time, that is the time taken for the drum to start from the slurry tank, go round and finally reach the slurry tank, is made up of 4 steps. One is called the filtration time, second is the washing time, drying time, finally the discharge time. All these add up to get a cycle time. So we can still use the Darcys law for the calculating the filtration time. So if you remember from our old previous slides, you will get a relation for the cake time taken for the cake to form or to filter a slurry of volume Vf A is the area which is dipped inside your slurry tank, rho naught as you know is the mass of the solid per volume, mu is the viscosity, and this is the resistivity. Here we have assumed compressible solids, that is why you have delta P raised to the power 1 minus S, okay, do not forget that. If there is no compressibility, then that term will disappear, okay, the S term will become 0. Remember that there is cake formed only when the drum is dipped inside the slurry tank, whereas when the drum is outside the slurry tank there is no new cake that is being formed, the cake is getting washed, cake is getting dried, cake is getting cut. So during the first stage when the drum is inside the slurry tank, we can still use the Darcys law relationship as we derived previously, and as you can see it is a function of amount of liquid or the slurry that is being filtered, it is a function of the area inversely proportional to the area, it is a function of the delta P. Because we have assumed a compressible solid, we got this term S. If the solid is not compressible, we can just omit this S, or S becomes 0, and these are the physical property of the liquid as well as the slurry density, okay. Now you want to calculate how much solvent or how much water is required to wash the cake so that we can purify the cake to a high level, or we can remove the amount of impurity present. So you have an empirical relationship that relates the amount of wash liquid required and the amount of washing efficiency and the amount of impurity that is present before washing and after washing. So this is an empirical relationship based on lot of experience. So we cannot derive this particular relationship from fundamentals, okay. So this relationship, as you can see, says R is the impurity remaining after the wash divided by impurity that is originally present in the cake before the wash, okay. R, this is equal to 1 minus epsilon raised to the power n. Epsilon is the washing efficiency of the cake. Generally we can take it as it is a function of the equipment, so generally you can take it as 70%, that means 0.7. Now this is raised to the power of n. N is the volume of wash liquid divided by volume of liquid retained in the cake. Because this is a solid, the solid will always retain some amount of liquid, that depends upon the amount of wash liquid we use, right. So N is a function of volume of wash liquid divided by volume of liquid retained in the cake. All these are related to the impurity remaining after the wash. So if I know this term R, I can calculate N assuming epsilon to be around 70%. If I know N, I can calculate R. So this is an empirical relationship, so that it is not calculated based on certain fundamental principles, but this is based more on experience. So if I know N, that means volume of wash liquid I am adding to the volume of liquid retained in the cake. Now volume of liquid retained in the cake is a function of the physico chemical properties of the liquid and the solid cake. Volume of wash liquid is a function of the solubility of the impurity. Now this is related to R on the left hand side. R is the impurity remaining after the wash and impurity that is present originally. Now this is a function of so many factors. This is a function of the solubility of the impurity in the washing up liquid, it is a function of the efficiency of your equipment, it is a function of how much of liquid that is retained by the cake. So it is a very simple relationship, r equal to 1 minus epsilon raised to the power n, and it is an empirical relationship as I said. So using this relationship we can calculate either knowing the right hand side we can calculate the left hand side, or knowing the left hand side we can calculate the right hand side. Now there is another relationship, this is again an empirical relationship, this is TW divided by TF. TW is the time required for the washing, TF is the time for filtration, that is the time when the drum is inside the slurry tank, TW is the time for washing. So TW by TF is equal to 2NF. As you know, N is related, is given here, N is the volume of washed liquid divided by the volume of liquid retained by the cake, F is the volume of washed liquid divided by volume of filtrate. Again this is an empirical relationship. So if I know the right hand side I can calculate the left hand side TW, or if I know TW, if I know N I can calculate the F. So you see this two equations, one is r equal to 1 minus epsilon raised to the power n, and TW divided by TF is equal to 2NF, both are empirical relationship and they relate several properties of the cake, the impurity present, the solubility of the impurity in the washing liquid, the efficiency of your rotating drum filter, the amount of liquid retained by the solid cake, and so on. So these are all related to the physico chemical properties of the impurity, the physical properties of your cake as against the physical properties of the washing up liquid you are using it. So using these two relationship we can calculate many terms required for your design, how much of washing up liquid that I require to remove the impurity present in my cake from certain value, say from 10% to 1%, how much of washing up liquid I will require. So I can use these equations to calculate that, or I can say if I have 10% impurity and I add so many 1000 liters of washing up liquid, how much will be the reduction in the impurity from 10% to what value. So I can use these two relationships, they are very simple relationship to calculate the impurity profile depending upon the amount of washing up liquid I am using and depending upon the physico chemical properties of the impurity as well as the cake. We will look at some problems in the next class. Okay. Now the next design which we saw in the previous is centrifuge. Centrifuge achieves its driving force through the application of a high rotational speed, and because of these centrifugal forces solids get thrown out to these walls and the liquid flows right through the center, and that is how you achieve a solid liquid separation. So if you look at a tubular bowel centrifuge, they generally they operate at batch conditions, the foaming could be a big problem in this. So if you take a solid which is entering the centrifuge, two things are happening to the solid. One is because of the movement of the liquid the solids travel along the axis of the centrifuge, number 1. Number 2, because of the centrifugal forces they are thrown at the wall of the centrifuge, and this is a function of the radius, that is location, radial location of this solid. Okay. So two things are happening, one is the solids encounter a force along the axis because of the bulk flow, and the solids encounter a force which is the centrifugal force because of the rotation of the centrifuge, which is a function of the radial location of the particle. So if you consider these, the movement of the in the z direction, that is along the axis, and the movement in the r direction, that is a function of the radial position, we have two equations dz by dt and we have another relationship dr by dt. So we can combine all these relationships to arrive at a final equation Q, that is the throughput through the centrifuge, a tubular bowel centrifuge, as a function of R naught, which is the bowel radius, R1 this is the liquid surface radius, L is the length of the tube, omega is the angular velocity, okay, and V is the terminal settling velocity. Now if you assume R naught and R1, that is the radius of the bowel and the radius of the liquid are almost equal and they are equal to R, then the equation gets very simplified to this form: Q equal to Vg, that is the terminal settling velocity of the solid, L is the length of the centrifuge, R is the radius of the centrifuge, we can take it as omega is the angular velocity divided by G. So what does this mean? Throughput is a function of the settling velocity and these are related to the hardware of the centrifuge as well as the operating angular velocity. Now as you know that settling velocity is a function of the physical properties of the solid and the liquid, like the diameter of the solid, the density of the solid, the density of the liquid, viscosity of the liquid. Because I talked about it about couple of classes back, terminal settling velocity is based on the Stokes law, okay. So the throughput through this particular centrifuge is a function of the particle settling velocity, which is a function of physical properties of the solid and liquid and the hardware and the operating conditions of the centrifuge. Very simple, we can say. Now let us look at the disc stack centrifuge. Again I talked about it in the previous class. This contains several discs at a certain angle. So the liquid that enters from the bottom, because of this disc, get focused towards the outer periphery of the centrifuge. The solids get stuck to these outer walls of the centrifuge, whereas the liquid turns and then goes out here and the solids are collected here. So the angle of the discs and the number of discs decides the efficiency of the centrifugal operation, and so let us not go into the derivation of this particular equation, but ultimately you end up with an equation of this form. Again you see Q, the throughput through the centrifuge, is a function of Vg, Vg is the terminal settling velocity, and these are parameters which describe the hardware of the disc centrifuge, and omega is your rotational velocity. So once again, just like your previous relationship for a bowel centrifuge, we have the throughput as a function of the terminal settling velocity and the hardware parameters. Whether it is a disc centrifuge or whether it is a bowel centrifuge, we have throughput on the left hand side as a function of the terminal settling velocity and the hardware parameters, and the terminal settling velocity is once again a function of the physical properties of the solid as well as the physical properties of the liquid. So very simple, so it is directly related to the hardware parameters as well as the physico chemical properties of the liquid and the solid which you are trying to remove. Okay, let us look at a simple problem which tries to give you some idea about the throughput through a centrifuge. Imagine I am using a bowel centrifuge to harvest cells. Okay, then what do I do is I take the cells, break the cells, so the diameter of the cells become half. Okay, The viscosity also doubles, as I talked about it long time back. The release of intracellular materials, DNA, RNA generally raises the viscosity. So the viscosity is doubling and the particles have become half, and now I use the same centrifuge to once again separate the solid and the liquid. So what will be the throughput? So initially I have the centrifuge where the particles are of certain diameter d and viscosity is of certain viscosity mu. Now the diameter has become d by 2, viscosity has become 2 mu. So what will be the throughput? Now you have to recall your Stokes law if you want to calculate what will be the throughput. Okay. Now nothing is happening to the hardware, I am maintaining the same RPM of the, and I am using the same centrifuge, so nothing is happening to the hardware, only the terminal settling velocity term changes. So my throughput will be depending upon the parameters inside my terminal settling velocity. So if you recall your equation, throughput is a function of particle settling velocity and hardware, and I am not doing anything to the hardware, I am just changing the settling velocity because the particle size has become half and the viscosity has doubled. Okay. So if you recall your Stokes law, you have the viscosity term here and the diameter is square term. So viscosity has become 2 mu and the diameter has become d by 2 square. So the velocity from original value has changed because of the change in diameter as well as the change in viscosity, and that is going to affect my throughput, which is on the left hand side. So what is going to happen? Because the particles have gone down in size, so the viscosity or the velocity will change in a squared fashion, viscosity has doubled, so again the velocity is going to change in that fashion. So new throughput will be equal to old throughput, because the particles have become half, I have put half squared because diameter square term is coming here. Now viscosity has doubled, so I have put a 2 term in the denominator. So you look at 1 by 2 square become 1 by 4, there is a 2 here, so it becomes 1 by 8. So what happens? The new throughput has gone down by a factor of 8. Okay, so old throughput divided by 8, because the particle has become smaller and the viscosity has doubled. So what do we have to do? If you want to use the same equipment, either you accept that the throughput will go down, or I have to change my RPM so that I am able to increase my throughput. You might not be able to increase it by a factor of 8, but you may be able to increase it, double it or triple it, or I may have to go through some other Bowl centrifuge so that I can maintain the same throughput. So that is what normally is practiced. People do not use the same centrifuge and hope to get the same throughput, but they will like to go to some other equipment with the different dimensions or with different angular velocities. Okay.